This is the pre-lab for the synthesis of an aldol condensation product. This week you will perform a Claisen condensation with the aldehyde and ketone you were given during the last laboratory experiment. In this presentation we will cover the typical material, including the pre-lab assignment, safety information, goals and methods of the experiment, background information about the aldol condensation reaction, how to properly conduct the experiment, how to clean up, and lastly, some key points about the post-lab analysis questions. Before coming to lab, make sure you read the assigned sections from Techniques in Organic Chemistry and your Organic Chemistry textbook. You should also set up your lab notebook. This week's experiment is a little different than others in that you will be developing a procedure using one given to you in the lab manual as a guideline. Keep in mind, this experiment will extend over 2 weeks and count as 2 experiments. For your safety, understand that the aldehydes and ketones are irritants and corrosive. The 50% sodium hydroxide solution you will be making up is highly corrosive and will cause burns to the skin. Most importantly, the aldol condensates have unknown toxicity. Because of this, you should wear gloves and goggles at all times. The main goal of this experiment will be to develop and refine a procedure for carrying out an aldol condensation with the aldehyde and ketone you were assigned. To do this, you will react the aldehyde and ketone under basic conditions. You will then vary the reaction conditions to try to optimize the product formation and yield. You will then recrystallize your product and analyze using melting point and proton NMR. One key aspect of aldehydes and ketones is their acidic nature. As you will learn in lecture, the carbonyl inductively withdraws electron density from the adjacent carbon, called the alpha carbon. This increases the acidity of the hydrogens attached to that carbon, such that a base, like hydroxide, can remove a proton. In the process, the electrons can be delocalized onto the carbonyl oxygen, resulting in an enolate ion. The pKa of aldehydes is similar to water, which leads to an equilibrium constant of about 1, meaning there will be an equal mixture of enolate and aldehyde in this particular solution. Because of this, the enolate can act as a nucleophile and the aldehyde can act as an electrophile. The enolate undergoes addition to the carbonyl group. The resulting alkoxide then can abstract a proton from water to give the aldol and regenerate the hydroxide ion. If the aldol created still has an alpha hydrogen remaining, deprotonation can occur with hydroxide. In the presence of heat, the resulting enolate can undergo an elimination of the hydroxide ion to form an alpha-beta unsaturated aldehyde. In this experiment, you will be performing a specific type of aldol condensation, called a Claisen-Schmidt condensation, a mixed aldol condensation between an aromatic aldehyde and a ketone, which is what you were given. Aromatic aldehydes have no alpha hydrogens and cannot form enolates. The ketones we will be using have 2 sets of alpha hydrogens, one on each side of the carbonyl. Both sides can undergo condensation in the presence of base to yield a bis adduct. Because of this, you need 2 moles of aldehyde for every 1 mole of ketone used. A general procedure of an aldol condensation is provided in the lab manual. You will want to use this as a guideline for your specific reaction. Make sure you think about the difference in stoichiometry between your reaction and that provided in the general procedure. The first step in lab will be to test your procedure to make sure you get product formation. Isolate your crude product and take a mass. This will be your initial starting point. The point of lab is to see if you can improve the yield and purity. To do this, you can vary parameters such as temperature, stoichiometry, and reaction time. Make sure you change only one variant at a time. Of particular note, the procedure describes monitoring the reaction by TLC. This is unnecessary and will be omitted from the procedure. Run as many variations as time allows and obtain a mass for each trial to track the success or failure of your modifications. Once you are convinced you cannot obtain a higher yield, try purifying the product by recrystallization. Take a melting point of both your crude and recrystallized product to determine if recrystallization is even necessary. You can then compare your melting point to a table of known melting points, which can be found on Sakai. Data organization is critical in this experiment. Make sure you divide your notebook into clearly labeled sections. Include a reagent table, yields, and observations for each trial, along with any melting points you obtain. Highlight each modification you make along the way. You will be graded based on how well you construct your lab report. When you are finished with the reaction, make sure you clean up properly. Place any reaction filtrates into a basic waste container, any recrystallization filtrates into an organic waste container, and all solids in a solid waste container. Before you answer any of the analysis questions in your notebook, you need to first summarize your trials in a table. This makes it much easier to see your modifications and the resulting yield you obtained. One of the questions tells you to write out a procedure. Be as detailed as possible, using actual masses and volumes of materials used, and include reaction time and temperature. Pretend as if you want your friend to replicate your results as close as possible, and write your procedure accordingly. Remember, you have 2 weeks to complete this experiment, so use your time wisely and have fun.